DVB receiver. So let's look at some technical work going on in the DVB receiver channel on the Phase4 ground Slack. Implementing an open source version of DVB-S2 and DVB-S2X receive is a very ambitious goal, and Charles Brain, G4GUO, has been particularly active here, with Jan Schiefer, AC7TD, Ron Economos, W7RZ, Wally Ritchie, WU1Y, and many others helping and participating. Charles' implementation uses a GPU, or graphical processing unit, to handle the heavy computation. His successful implementation of LDPC forward error correction decoding was demonstrated at the AMSAT Space Symposium in October 2017. GPUs get their computational horsepower from massive parallelism, and this has some interesting implications for radio performance. In order to take full advantage of the parallel processors, Charles has it configured to process a batch of up to 128 frames at once. All the frames have to be the same mod code, modulation and coding. Our air interface calls for the use of adaptive coding and modulation, or ACM, so that we can accommodate a wide variety of ground station types and capabilities and take full advantage of higher performance ground stations. With ACM, the downlink contains a mix of frames with different modulations and coding formats. This means that a GPU version, or any radio with parallel processing, may need some extra accommodations. If you want to read more about adaptive coding and modulation for Phase4 ground, here's a link to our paper on GitHub in the notes. With this kind of receiver, there's a fundamental trade-off between GPU utilization efficiency, how many of the CPU cores we keep busy, and latency, which is how much extra delay is caused by holding back frames until we have a full batch. If our goal is to keep the GPUs busy to maximize the compute speed, then we have to wait until 128 frames of the same mod code have arrived before we can start to process any of them. All 128 frames then come out of the receiver in a burst. The 128th frame is only delayed by the necessary minimum processing time, but the first frame has been delayed by an additional 127 frame times, or more if some of the intervening frames had a different mod code. So the first question is, do we need to keep all the GPU cores busy? Well, probably not. It depends on just how fast the GPU cores can process frames compared to the frame rate on the downlink. Maybe we only need to keep a fraction of the GPUs busy in order to keep up with the downlink. So maybe the magic number isn't really 128, but something smaller. The only way we'll find out for sure is to complete the GPU-based receiver implementation and benchmark it. The second question is, just how bad is the extra delay? If we stick with 128 frames to a batch, how much delay is that? Well, our air interface calls for using so-called short frames, as recommended for near space communications by CCSDS, the Consultative Committee for Space Data Systems. Short frames in DVB-S2 and DVB-S2X are 16,200 bits long. To turn that into a duration, we need to know the effective bit rate of the channel. Now we've chosen a baseline bandwidth of 10 MHz and a 20% roll-off, which results in a fixed channel symbol rate of 8.33333 megasymbols per second. The formula is bandwidth in hertz equals 1.2 times the carrier symbol rate in hertz, where the 0.2 in 1.2 comes from the 20% roll-off figure. By the way, 20% roll-off is a good middle-of-the-road number. Industry groups say that DVB-S2 carriers below about 10 megasymbols per second really need a guard band of at least 10% roll-off. The older DVB-S standard specified a fixed roll-off of 35%, and the newer DVB-S2X goes all the way down to 5% roll-off. So we have our fixed symbol rate. With adaptive coding and modulation, the code rate and the modulation order change. That means that the data rate changes depending on how much extra help your receiver is going to need to successfully decode a frame. We've chosen 6 mod codes for our initial implementation of ACM. If you work out the math, nominal data rates for these mod codes at our baseline symbol rate range from 4.04 megabits per second to 21.067 megabits per second. There's a table in the notes. The delay is longest at the lower data rate, 4.054 megabits per second. 128 frames of 16,200 bits each is just over 2 million bits, or about half a second. That's assuming we transmit nothing but the slowest mod code. The delay could be much longer if ACM inserts lots of other frames of other types. On the other end, 128 short frames at the highest data rate takes just 1/10 of a second. But again, that's a lower bound if we allow ACM to insert other frames. And these delays are on top of all the other delays in the system. For a Phase 4 satellite in GEO, there's already 1/4 of a second just in propagation delay. Adding 1/10 of a second to that might not be a big deal. Adding 1/2 a second might be. It would depend on the application. For lower orbits or for terrestrial systems, the calculation is, of course, different. We can't improve these lower bounds, except by decreasing the number of frames we process in parallel. And we can only do that by making the processing faster, either by even more clever coding or by waiting for GPU hardware to just get faster. We can't improve the latency by just arbitrarily reducing the parallelism. If we go below the magic number required to keep up with the channel data rate, we'll still end up paying the latency price for all those frames we had to skip in the meantime, just in order to keep up. On the other hand, we can try to avoid making the latency problem worse than it has to be. The simplest way to do that would be to fall back from ACM to CCM, constant coding and modulation. That is, transmit all frames with the same mod code. Unfortunately, by doing that, we give up some very desirable flexibility in ground station designs. Another simple approach would be to just accept that the parallel GPU-based implementation is only suitable for applications that aren't real sensitive to latency. Applications like file transfer care more about the overall data rate than about latency, for instance. And there's room here for us to invent a more complicated solution to take these trade-offs into account. Some sort of dynamic scheduling algorithm that takes the latency requirements of each data stream into account could be devised to suit our needs. And that's called quality of service, or QoS, and it's a can of worms. Join the discussion on the DVB receiver channel on Phase4 Ground Slack. Snickerdoodle. Finally, here's an unboxing and setup of another option for learning and programming FPGAs. This is a Snickerdoodle Black with a breakout board. It has a Xilinx Zinc 7020 and lots of interfaces and plenty of GPIOs exposed.
Slack for engineering discussion and planning. It's been a success. Here's some analytics on all our channels, followed by an engineering update from DVB receiver. This graph is messages sent since we established the account, 40,912 of them. There are spikes over time and a trend up since early January. On top is where people are reading. The purple is public channels. The red is direct messages between members. The black on the far right represents a new private channel. This private channel is for the badge build process for JOCO. We're keeping it private as to not reveal the puzzles and surprises to the people that'll go on the cruise. The bottom graph is where messages are sent. So notice the difference? There are a lot of people following along in the public channels. On the top is messages sent over the past 30 days. On the bottom is where people are reading those messages over the past 30 days. On the top is the messages sent in public channels and direct messages. On the bottom is the one private channel, broken out. There's a lot of talking going on in the private channel. We are very much looking forward to everyone seeing the results of all this work very soon.